开始去找你。
要开始。
So you have 5 minutes.
I think I'll有一个设备。OK。
Wait. Okay, opponent change the reporter.
We like to challenge problem number 4.
Number 4.
So, we accept.
We're going to have 5 minutes to prepare. Because you are not the reporter now, the opponent can change the keep. Or you can have another report.
We can reject.
Reject. Okay. Yes, because the reporter cannot represent.
I cannot present 3 times. This is my topic. I presented 3 times. Okay, so.
We start again. Good. 20 pages.
Okay.
From the challenge. You have challenged problem 3, right?
Yeah.
Maybe check.
Every no?
No.
Yeah.
Yeah.
One last reject.
哦，是这样子哦，是缝算吗？缝读书因
No reject.
因为我不能比赛3次了，
哦，
因为我自己3次了，
他们自己选择，他们因为不能上来自己选择。
So his challenge is locating himself in a race. 哦，
on the spaghetti accelerator. So the problem statement is that when a piece of spaghetti is pushed into a vent tube, small debris is going to be ejected from the other side at a surprisingly high speed, and you want to investigate this phenomenon. A couple of factors we're going to talk about is about the angle of the tube as well as the length of each spaghetti fragment that is ejected. Here's our structure. First is observations. Here we have a video of what actually happens when we put the spaghetti through the tube. We can see that pieces will fly out, and we observe that while a piece of spaghetti is pushed against an angled surface, there's going to be compression forces and tension forces. Compression forces are the ones that we see on the top here, where the arrows are pointing inwards, and tension forces are the ones where spaghetti are the ones where the arrows are pointing outwards, essentially where the outside edge of the spaghetti is being stretched. So what happens when the spaghetti snaps is that the forces make the spaghetti spin and rapidly fly off, where potential energy, especially potential elastic energy, is converted to kinetic energy. Meanwhile, the tube is only there to simply direct the energy to make the spaghetti go in a certain direction. So now we're moving on to our theoretical models, where we have two theoretical models. The first is about bending energy and energy stored in the spaghetti while bending, and the second is about axial stress energy on the spaghetti, like going this way. Both of these models will aim to provide explanations for what's happening. First, we start with the bending energy, specifically the general strain energy formula, where sigma is the stress. It is the internal force that occurs when external forces are applied to a beam. And epsilon is the strain. It is the change in length when external forces are applied. And this U represents the energy, the energy density, and energy per a given volume. So there's a couple substitutions for sigma and for epsilon. We can see it here. M is the bending moment. It is the force that causes something to bend. I is the moment of inertia, which measures how much the beam resists rotational acceleration. Y is the distance of the bent beam to that of its neutral axis, essentially how far it's being bent. E is Young's modulus, which is a constant, and it's about how deformable this beam is. It depends on each material. So here we substitute it in and integrate it over the area to get the energy in the entire cross section, and to get this model for the energy. And that model was and that model used the Euler-Bernoulli beam equation, which is a simplified version of it, and it assumes a small amount of bending. Now we believe that we shouldn't have this assumption, so this is the full expanded equation for our model. Our second model is about axial force, essentially the force on the spaghetti, longitudinally. In the bent tube, the spaghetti is not going to experience the same axial force across the entire cross section, right? The force on top is going to be a lot stronger than the force on the bottom, as we see here. So the goal is to figure out the force along the spaghetti at a certain position along its cross section, which leads us to the formula for linear interpolation, where y is where y0 is the bottom force, and x0 is 0, because that's essentially where the starting point is, and then we can convert it to this force equation as we see here. So again, we revisit the general strain energy formula. We substitute again, and using linear interpolation to get this model down here, where d, as we can see there, is the d is the diameter of the spaghetti. And both of these models aim to explain the same phenomenon, which leads me on to my experimentation and discussion. First, a little bit of data about the spaghetti. The average length of each piece was about 0.25 meters, 25 centimeters. Average diameter was about 1.76 millimeters, and the mass per unit length is 0.0037 kilograms per meter, which assumes uniformity along each piece of spaghetti. So here's our experimental setup, right? We have a rail where a car moving at constant velocity is traveling on. That car carries a piece of spaghetti, and as the car goes down the rail, the piece of spaghetti is going to go into an angled tube that is fixed. a piece of string is going to pull that car and the motor is going to drive that piece of string in order to make the car go down like that. Now, remember that for the axial model, we had to calculate the force on the piece of spaghetti itself. So what we did is that we attached a force sensor to that angled tube in order to calculate the force that the force exerted on the spaghetti when the spaghetti goes through. We have our tube units here. F30 means the force for pushing the spaghetti through a 30-degree tube, essentially a shallower tube, and then force 45 is for a 0.48. Force 45 is for a 45-degree tube. Next, earlier I talked about Young's modulus, and here's how we calculated it. We used this equation over here, which is Young's modulus for a beam. And so the way we did it was that we hung different weights off the piece of spaghetti, as we see in the diagram here. We calculated how much it would depress, like how much the beam would be deformed based on what mass it would get, and then we used that in order to calculate Young's modulus. Another thing that we have to calculate is the moment of inertia, which is explained by this formula here, where r is the radius of the spaghetti. It's a bit simpler, just substitute radius in there. Meanwhile, and now so let's say we have a polynomial equation. I'll explain why we have this later. Essentially, we can do differentiation to get these two values for the coefficients of these polynomial equations. The reason why we want to do that is we'll substitute it into our general formula there. And the reason why we're doing all this in the first place is because we can find the polynomial equation of each piece of spaghetti. As we can see here in this 3D frame, the spaghetti is bent right before it breaks, meaning that we can track each point along the spaghetti to form a polynomial equation like this. And we can see that the constants, again, can be substituted into our calculus, into our model that we showed earlier, which means that we can see that it can be substituted in, which will help in our calculations. This is the polynomial equation for the 30-degree tube. So now we're going to compare our theory to our actual results, our models to what we actually got. And here's for the 30-degree tube, which I realize is a bit this is a bit of an odd name, but essentially it's the shallower tube that it's a shallower tube, and we can see that here we have the velocity of the ejected piece. It's the velocity of the ejected piece of spaghetti, and we have the length of each ejected piece of spaghetti, and then we took the average. And the reason why we're doing this is so that we can calculate the energy that we get at the end. So the data that I showed earlier is going to go into here, actual energy, which we calculate using 1/2 mv squared. And so 1/2 remember how earlier I said that the density, that the spaghetti was 0.0037 kilograms per meter. This is why I have that value, because we have the length of each ejected fragment. We have like the almost like the density of the spaghetti. So we can multiply that together to get the mass. Meanwhile, there's the velocity squared to get to get 1.7395 times 10 to the power -3 joules. So we can see our two theoretical models up here, where we substituted in our polynomial equations, and we substituted in the force that we needed to the force of the spaghetti going through. And notice how here, for the bending, I multiplied the length of each spaghetti fragment by 2, and I'll explain why here. Why did I double the length? Well, because that formula earlier is about the energy stored throughout the length of the bending of the spaghetti. You can like this length, the bending length. However, the issue is that in our calculations, in our experiment, we're measuring the length of the spaghetti fragments. We're measuring like how we're measuring the length of each ejected piece itself, which is not equal to the length of the piece of spaghetti that bends. Therefore, we multiplied it by 2 in order to get this the actual length of each piece of spaghetti that bends. Here's our data for the 45-degree tube, sharper angle tube, and again some more calculations for the energy. Same idea as before. So here's a graph showing our overall comparing our theory to our actual results. So we can see that that both models of determining the spaghetti's energy are about double of what the actual energy that we calculated it is. And the reason why we believe this is because energy can be lost, and we'll elaborate on that later. These error bars that we see here are determined by the standard deviation of the energy that we got. And it's important to keep in mind here that for these two experiments, we did not keep the input velocity constant between 30 and 45 degrees. We will do that later. By later in here. So here we're trying to calculate various parameters, how various parameters affect the energy of the ejected spaghetti. So here we can compare the two different tube angles. We kept the input velocity constant, and we can see what effect the angle has on energy. Again, calculated energy using the same idea as before, and we can see that for these, we can see that the theoretical and both theoretical models end up calculating a lot more than what the actual output energy is. Meanwhile, the output energy for a sharper tube is higher, and we believe this is because, like, when the spaghetti is deformed more, obviously it's going to have more strain energy, which means that there's more energy, which means that it gets ejected faster. This is about how initial velocity affects energy. To vary the initial velocity, we vary the voltage of the motor that would drive the spaghetti, that will drive the part forward. Again, error bars determined by standard deviation. And earlier I talked about the length of each spaghetti fragment, how it determines velocity. And here we can see that the results are inconclusive. There's very little correlation between the length of each fragment and the velocity, meaning that we believe other factors like the angle matter more. Here's some potential source of error. We said that all pieces are the same and perfectly straight, and there's some errors which are method 2, where the energy can be lost to friction in the tube, as well as how the whole diameter of the tube is more than the spaghetti.
Okay, so first, in terms of page, page 20. So why did you multiply by 2?
You mean of the length?
Yeah.
Well, like I elaborated earlier, we can see the formula I used earlier is about the length of the bending, right? It's about energy stored throughout the length of the spaghetti while it's being bent.
Okay. So did you calculate the energy transfer ratio?
We didn't get the ratio.
No. Okay. Next question. So did you calculate the stored energy in the spaghetti?
Yeah, the two models are going to calculate the stored energy.
Okay, so you did calculate. Then what's the speed of, because in your setup, you use like a car, so what's the speed of it? Did you calculate the speed?
Yes, we calculated the speed. Here it is. You can see that here we have the input velocity. There's two input velocities that we used.
Or you put two variables on the speed.
Yeah,
Okay.
two different speeds that we used.
Okay. Then I'd like to ask, so you on the beam theory page, okay, next to the page.
Is it here?
Yes. So did you consider that? Did you assume that the beam theory is under a steady condition?
Yeah.
Okay. Now, can you turn to page? Okay, so you use just to verify, you use parabolic line to fit the. You use that to fit the shape of the spaghetti.
Yeah, we track each one.
Then, so in terms of page where you said you use 2 forces, the 2 forces is really. So you assume that the two forces acting on the spaghetti is different, yes?
No, we don't think. Wait, no.
Okay, thank you.
Want to collect more, just get black smell.
Okay, start.
Okay, so I'm the opponent for problem number 9. And so just for a recap, the key point of the reporter's question is the factor that includes the speed and then the bending angle. And for the observation theory, I think the reporter has used Euler's working theory to calculate the energy. And then for experiment, they use a slide to input the spaghetti and to measure the Young's modulus. And then they measure the force in the tube. And then for the bend, they calculate the bending angle input velocity and how does that affect on the exit velocity. And for the conclusion, they say that the larger bending angle causes a larger energy. As for the observation, they have a clear observation about the phenomenon and the video, and they have a very clear video demonstration. As for the cons, I think they lack of interpretation about the times 2 of results. As for the experiment, they have well-controlled experiment and have the quantifiable measurements about the part. Yes, and they have a clear graph. As for the cons, they use a quadratic equation to fit the Gibbs equation, and then the friction may cause deviation. And for later on discussions, I would like to discuss the point of the beam theory, and then plus the thing that they didn't calculate, which is the energy transfer ratio, and then for the definition about the axial energy. And for, yes. Okay, so that's all. I would like to skip to the discussion. So first, because you mentioned earlier, you use a beam theory, and then you said that the condition is a steady condition. However, since you use a sliding part as an input speed, how is that a steady condition? Can you elaborate more on that?
Well, we tracked the velocity of the sliding part as it went through the tube, and we noticed that the velocity stays pretty much the same throughout. There isn't really much of an acceleration or deceleration as the car goes.
Okay, so when you're accelerating the car, how does that process cause the spaghetti to break? Does it break in the middle when the car is still sliding, or when the car suddenly stops and then the spaghetti breaks?
No, like the car while the car is the spaghetti while mounted on the car, it is going to go through the tube before the car actually decelerates or stops or anything like that.
So when does the spaghetti break in that process?
So the spaghetti breaks while the car is still going at its regular velocity.
It's when the car is still moving.
Yes.
No, I don't think that's actually the case because you have to consider dynamic hardening. It means that when the car is moving, when the input speed is changing, that causes the stiffness of the spaghetti to change, and that causes higher stiffness. So when the car actually stops, that moment, I think that's the actual breaking point of the spaghetti.
Well, okay, you said that the stiffness of the spaghetti will change based on the car. We don't believe that's true.
Because based on the input speed, because that's called it's a thing called dynamic hardening. When the product, the spaghetti is moving at a speed, it's hardened its stiffness.
Well, we calculated like the stiffness and like these factors using Young's modulus and then the moment of inertia. These stays
You use the calculation about the Young's modulus on a steady state. However, since you use a car as an input speed, that's not a steady state. Therefore, and that process causes the stiffness of the spaghetti to change. That's what I'm trying to say. And then next point, I would like to move on the quadratic, the x squared, the provided logic fit. And can you elaborate more on the physics behind this? Because it seems like you use a living like cubic relation between the two. Can you elaborate more on the physics background?
Well, we can see that when the spaghetti goes into the tube, there's going to be it won't just automatically break. For our tube, because it was 3D printed, there's a bit of friction in here, which is one of the sources of error. But the thing about the friction is that it keeps the spaghetti from sliding further forward while it's bending. So essentially, this is just a equation for what the spaghetti looks like while it is bending.
So you're saying that the cubic, the square function is due to friction, or is there a physical meaning why is it square, or not a fourth relation, or not a third relation?
Well, it can be to any degree, right? It can be to the third or the fourth degree. But the reason why we chose the second degree is because of this, earlier which I said, which we can substitute into our general formula.
Can you move it to the the big equals is 4 times divided by this should be equal to like this, right? This is A over 4. Since because this is the force of the spaghetti. So there's the force inside of the spaghetti. And then since this is since instead of this should be 0. Right? So then if a derivative function goes to 0, then u should be the 3 cubic relation, not a square relation. So I think well, based on physics, I think it should be a 3 degree relation, not a cubic relation. Yes. And then I'll move on to the energy transfer ratio. The stored energy as well. So instead of calculate the stored energy in the bending spaghetti, can you elaborate more on that? Which part of the stored energy are you talking about? Is it the entire spaghetti?
Well, we believe that what the spaghetti looks like is that, okay, so the concept when we mounted our spaghetti to the car, there was a portion that was like on the car mounted, and there was a portion that was
Yes.
and we're only going to calculate about this part.
So,
because one of the reasons, because we mounted it on the car, we mounted a piece on the
So
car
you can consider
that
this.
stays perfectly straight.
Okay, so let's focus on this. Right. So you can calculate this. Then so let's say this is a 2. And this is where you put inside. Let's say this, right? So there's the 3 contact points. And see there's 3 forces.
Well, in our experiments, what we noticed is that oftentimes, like the spaghetti is often bent like this. So that often isn't this third point.
Yes, it's curved. That's what. Yes, it is. Okay.
not gonna touch.
Then where's the breaking point of the spaghetti in this process? Where?
Well, in our experiment, we approximated it to about the midpoint.
Around the midpoint.
Where that is, it's something that's not exactly the midpoint, and that can be a source of error.
So,
But
then
we approximated it to about the midpoint.
so what causes the spaghetti when it exceeds? Is there a bounding condition for the spaghetti to break?
Yeah, it's just when like the bending force is too much of the spaghetti.
So, okay, so it's the maximum coverage. Okay, okay. So, we're moving back to the energy ratio, the energy storage. So you said you can take this stage, right? Here, I'd like to elaborate more on that because you said this is the tube, for example. And in your case, so the spaghetti is going to look like this, like that.
Close enough. It's It's
Okay,
it's
so
like-
so the storage energy, which part is the storage energy?
Well, we believe that
Is it from here to here? For example, this is the end, and then it goes to the car. Which part?
well we believe that the energy is stored like throughout this whole
So
piece
it's
already,
the-
but not the straight.
Not the straight part. So it's the part in the tube.
Yeah. Or like
But here's pretty straight. Here's pretty straight. So I'm concerned. What do you mean by the straight part?
Well, okay. By that I mean that in our experiment setup, when we mounted the car to the spaghetti, there was a piece of like fixed to the car. That
Yes,
was
because yeah,
So-
we're not talking about cars, right? You said it's not. That's not what.
Essentially, it's just
Yes,
outside
yes.
of the part. Outside of the part where the spaghetti is restricted, the part where the spaghetti is unrestricted, we are going to be able to do that.
So you calculate from here
Yeah.
to here as the entire spaghetti energy. And how? So these entire stored energy is transferred into the kinetic energy.
Well, if you saw from our data, a lot of the energy is lost, but like most of it is okay. But most of it is converted. But there's a lot of reasons why. First off, remember how in the beginning I showed how the spaghetti would spin around, right? And this means that when the spaghetti spins, it's going to hit the walls of the tube. It can lose energy that way because it's hitting the walls
No,
of the tube.
no. I think it's because when let's say this is the spaghetti, and then when let's say the spaghetti goes like this, then you said it breaks the middle part, right? Nearly the middle part, approximately the middle part. That's its operation. And this entire stored energy does not transfer completely into the degrees kinetic energy. What's actually is only this part, this portion of the stored energy is transferred into the kinetic energy. What happens to this part, however, this may cause like vibrations to the end of the tube. So I think that's the mechanism, that's the physics idea about this process.
Well, we believe that because there's, even though it brings here, we believe that a lot of the energy is still going to be, a lot of the energy stored from the tube is still going to be converted to kinetic energy because like because the spaghetti still has a lot of strain energy inside of it while bending, and when released, that energy is going to be transferred and it's going to be.
Okay. Well, okay, there's another thing. So can you move back to why you multiply by 2 by the page? And the page, where is it? 29. I think you multiply by 2. I think you mentioned you can multiply.
Here.
Why?
Well, again, because in our experiment, when you measured the piece of the spaghetti that broke off, it's like it's just a part of the spaghetti that broke off. But again, we multiply the energy throughout of the whole bending part, so we multiplied it by 2.
The whole bit. Yeah, so yes, that's why I think that can describe that. Why in your theory, why is there a huge energy loss? Because the energy is not transferred completely into kinetic energy. And I think it's important for this problem is to find the energy transfer ratio. Because for when there's the bending energy stored in the bending energy, and by this, when you find the energy transfer ratio, you can get the ideal kinetic
Okay, another thing about our experiment is that we're assuming that there's uniform energy density throughout this bending part, which means that we can use this to estimate about how much of the energy is transferred to this specific relation. But we can use uniform energy density as well to determine how much of the energy is transferred to the piece of debris.
So that's the end of the discussion. Thanks for it. For the conclusions, we first discussed about the multiply two problem in the page, and then we talked about the energy transfer rate from this problem. And later, we talked about the mechanisms that causes energy transfer in the process. And then in this report, he thinks that we have to calculate the entire energy, stored energy, and we think that it is not. The report has some misunderstood about the physics meaning about it. And then we talked about the cubic approximation about the population. So yeah, I think there's some deviation happened there, and I think that it's very useful. A cubic relation, not a square relation.
Reviewers.
Greetings. Did you consider the energy transfer ratio?
No, we didn't calculate the energy transfer ratio.
Okay. Why do you think that the energy transfer ratio is really important in this family?
Because it says because stored energy doesn't transfer completely.
Yeah.
So in order to quantify the kinetic energy, this is essential.
Okay, I see. So you have mentioned that in the experiment you use the car to push the spaghetti, but did you consider that maybe you can't control the hitting angle, the pushing angle?
You mean like the energy of the angle of the spaghetti going in?
Yeah.
Well, that's why we like earlier I said that we mounted the spaghetti pretty sure on the car to make sure that it doesn't go in at some weird angle. Okay.
So if they didn't control the hitting angle, then how will the return speed change? What do you think?
Change based on
The return speed.
change in speed.
Yeah.
Again, so the speed causes an energy hardening, which
Yeah.
it makes the stiffness of the spaghetti to harden. And so with fair speed, the stiffness will increase, and therefore it's harder for the spaghetti to break.
Okay. And did you consider the moisture of spaghetti?
Well, the moisture was one of the bullet points in my error analysis slide. The moisture can make the spaghetti a bit softer, which means that it's which can affect the constants such as Young's modulus, which can affect the results of the spaghetti over time. That is one of our sources of error.
Okay. So do you think that the moisture of spaghetti is really important?
Yes, because it causes different the properties of the spaghetti,
What property?
like the stiffness and other stuff.
Okay. Then, you have mentioned that you do the experiment about changing the angle, but you only have two data. How can you prove that the current, the result of your experiment is right?
Well, even though we only have those two angles, it is still a pretty big difference that we have still observed a pretty big difference between the two results. As you can see, the output energy increased a lot when it went to the 45
How do you
degree.
define big changes, big difference?
Well, here you can see the bars almost double, maybe even triple, and which I would say is a pretty big difference. And if you look at our theoretical model, you can see that more.
Okay, I see. So do you think that their two data is sufficient for getting the result, the right result? Okay. And there is a question for the opponent. And how would the speed of car impact the ejection speed of spaghetti?
The ejection speed of the
Yeah.
Time's up.
Okay, thank you.
自己有回报。
Greetings. I'm the reviewer from Team Ridiculous, and today I'm going to give an overall review of the problem number 15, spaghetti accelerator. So, in the previous discussion, we can discover that the pros of the reporter will be the clear notation, applicable theory, avoiding assumptions effectively, and also they do the experiments correspond to the theory. And there are also areas for improvements, such as the utilizing hand to conduct the experiments to push the spaghetti and stress the tube, neglecting the difference between the spaghetti. Tier units on page 20, and Young's motor is larger than the diamond. That is larger than about a million or 10,000. And every error bar in the graph of theory, per time control, fitting with projected function with no reason. Didn't consider the variation of the environmental humidity. The initial velocity is not zero. And for the comments for the opponents, we think that it is perspicacious, sagacious, and briefly summarize the reports. And there are also areas for improvement. They didn't seek to discuss effectively, and later following up the questions to give a different overview of the problem. So in the previous discussion, there is about the methodology to push the spaghetti, and the spaghetti press during the opponent said the spaghetti press during the steady state, and the reporter said that they disagree that. Reporters should try to figure out to fix the initial velocity to zero for further analysis. And many of the projected fitting, according to the differential equation the reporter provides, the data should be fitted in the projected function. And the reporter response is amid the error. We agree with the opponent. The fitting should have physical meaning instead of looking for the function, which fit perfectly. And for the energy transfer, the opponent said should have separated the spaghetti into two parts to evaluate the potential energy. The reporter answered that they consider the potential energy for the entire parts, but the energy somehow loss. We agree with the reporter. The Griffith fracture, the body caused the energy loss. And in the quick question I asked, we asked about did the reporter consider the energy transfer ratio, and they said they considered that. And also we asked the importance of moisture of the spaghetti, and then the reporter said that this is really important because they will impact the properties of spaghetti such as the Young's modulus. And also we talked about pushing the spaghetti mechanisms. That is the car. We asked about how they control the spinning angle of the spaghetti, so it will impact the result. And also, when it comes to the experiments about angle, the reporter only do about 2 data points to give a result about that independent variables. And we agree with the opponents because the data points, they lack of data points, so we can't just say that the result is just like the reporter said. And that will be my overall review. Thank you.
So first, you multiply the length by 2. Even though this isn't the exact measure of where the spaghetti is all broke, we believe that it's an approximation of the bending point that can be applied to most of our calculations, because it's usually halfway where the spaghetti breaks off. Furthermore, we can assume that there is uniform energy density throughout the spaghetti, which can be applied to the opponent's model if they wish, in order to calculate like what they believe is the kinetic energy of the spaghetti, of the piece of spaghetti being shot off. They addressed our polynomial degrees, and while higher degrees would be more accurate, we used a second-degree polynomial in order to be able to substitute it into a general formula in order to calculate the theoretical energy that would go into our spaghetti. We say that we only had 2 data points, but the thing is that we had multiple trials for each angle. As we showed above, we had 3 trials, and all of them support the same the same idea, which is that the greater the degree, the higher the energy that is going out. Furthermore, if we look at the our theory supports this as well. There's more force needed to push the spaghetti through a sharper angle too, and a sharper angle will increase the constant of the polynomial equation, again further increasing the energy. So even though there's only 2 angles, we believe that that's still enough to be able to say that a higher angle, like a sharper tube, is going to lead to more energy. And again, we addressed a couple sorts of errors, such as the moisture and the degree of the spaghetti going in. And while we agree that moisture will have an effect, we believe that it is still not good. We believe that other factors matter more. And the spaghetti is mounted, so there's not going to change anything.
Thank you again for the jury.
So the axial energy is for the, if I have a pencil here, the axial energy would be the energy applied this way. Not the bend energy, but applied directly to this end.
So using the screw.
Yes.
I saw the spaghetti is pretty big.
Well, as we saw earlier, the spaghetti still bends a lot while it's in the tube. So even though it's brittle, it can still bend quite a bit before breaking.
So you go to page 32. So you have the output energy. Is that the difference between the following two energies?
So these are the energies between the two degrees. This is the shallower 2 degree, and this is the sharper 2 degree. So so like these are just the sets of energy for each 2 degrees.
You have the bending energy and also the axial energy.
Yes.
One is right, one is correct. The blue is output energy. So how come the output energy is so small?
Well, again, this was addressed in our source of error where we believe that there's a lot of energy loss. A couple reasons. First off, there's a lot of friction in the tube that we use, which means that a lot of the energy of the spaghetti will be lost to friction instead of going out. Another reason is because the diameter of the hole in the tube was pretty large compared to the spaghetti, meaning, like I said earlier, that the spaghetti can sort of bounce around inside of the tube before it goes out, which again is
The Rafi, have you ever observed it carefully by very fast camera?
Sorry?
I mean, it's all your imagination. Have you observed it?
We haven't observed the piece of spaghetti bouncing around the tube, but what we have assumed, what we have saw is, yeah.
If you observe it, you can easily classify where's the energy go.
Well, what we have observed is that when there's no tube at all, when you just push the spaghetti against a table surface, it will spin a lot, and so therefore,
Any question?
Can you go back to the slide? I think you show the moment of inertia.
Yeah.
Okay. So I have a question to all three of you. Do you think this is right for the moment of inertia? High force times mass force. Can you please comment on this? Can all three of you comment on whether this moment of inertia is correct or not?
Well, we believe that.
Can you answer this quickly? Whether it's correct or not?
We believe that it's accurate, but there's also it's.
You believe it's correct. You believe it's correct. Can we move to the opponent? Do you agree whether this moment of inertia is correct?
No, I don't think so.
Then yeah, what's wrong?
I think it's the length.
The length. Okay. How about you? You got a particular opinion?
Well, I disagree with.
Okay, stop it. Any other question because we still don't know. Okay. Basically, we still need the time.
It's the density.
Okay. Okay. Any other question? Okay. That's it.
So I have one comment.
Okay.
In your
After the score, we can count.
okay.
Okay. Please. For the reporter. 5, 6, 6, 6, 7. For the reviewer. Oh, I'm sleeping. 7, 6, 7, 6, 7. For the reviewer. 5, 6, 6, 7, 7. Okay, that's the end. Oh! You want to come?
Yeah, my comment is on your conclusion. Actually,